Well, welcome back, folks. Looks like we can get started closing out, or starting out rather, our week 5. It's not Thursday yet. I've somehow time traveled in my head, but we'll be closing out week 5 shortly, it'll feel like. Big announcement is that we got through the very first exam, so congratulations on getting through it. Everyone should see your grade in Canvas as well as a scanned copy of your exam. And if anything seems missing, don't hesitate to reach out and I'll get that corrected right away. But this is pretty much going to be the week by week experience. What we did from week 1 through week 4, we just repeat in cycles. So looking further down into the schedule, when we're around, say, week 7, before we even get into week 8, we'll start constructing the sample exams material on the second exam. Right at the start of the week number 8, midterm week, I'll be contacting everyone in the class with instructions for scheduling the exam. But once you've gone through it once, it's going to be kind of the same experience as we go through exam 2, exam 3, and then eventually the final exam. They'll seem new, but really it's just a longer exam. It's comprehensive, but you'll know exactly what's on it, just like the other exams. Well, any last questions, folks, or comments to start us out today? Okay, well, we're working our way through chapter 3. We've just looked at the very first topic, introducing what is meant by a proposition. And section 3.2 is going to lay the foundation for other really big ideas we're going to be using in chapter 4, giving proofs, chapter 5 later on, proof by induction. First big idea was connecting all the way back from chapter 2, the very first definition of the entire course, the idea of a proposition. A proposition is a declarative statement, so not a question is the big trick question on example 1. A declarative statement means it's something we can assign unambiguously a definite true value or a definite false value, so some Boolean output. And we have just had a couple really fast versions of that question where 1, 2, 3 turns out to be composite. 3 divides it, so it's not prime. So it was a proposition and it gets the Boolean value of false. We said this one was not a proposition because it was just a question. And this was a proposition that turns out to be true since any integer can be re-expressed as a fraction. So this is a true subset relationship. We're going to expand quite a lot on this, but any questions or comments at the moment? Okay, with that initial idea of what we mean by a proposition, now we can start introducing the logical operators, and we'll have quite a lot in this section. We'll expand on them when we get into the next section, 3.3. But the first big one we'll take a look into is the not operator. So sometimes we'll just refer to this as negation, and this is the interesting syntax for it. Looks like just sort of a line that comes down like that, and whenever we see that, we're going to think not. So it's the negation of a proposition. If that proposition was true, like Z subset Q, then the negation of it would be false altogether. So it's true when the proposition is false, and it's false when the proposition is true. Next big operation is this one, the conjunction operation, or I'll often just say and for this one. Let's just start highlighting some of these elements. Whenever we see this, we often just read this as P and Q. This is a compound proposition now, and it's going to be true when both propositions P and Q are true at the same time. If one or the other or both are false, the whole entire thing becomes false. And the next one on the table is the disjunction, or I'll often just say the or operator. When we read through this, I often will just read this as P or Q. P or Q is going to be a new compound proposition. It'll be true if one or the other or both is true at the same time, potentially. If both of them are false, this is the only way we'll get a false out of this statement. So those are the 3 big operators to start off the notes. And we'll connect the dots when we think in terms of what we saw before. There's a kind of an amazing relationship between logic as we're defining it, propositional logic, and set theory at the same exact time. The carryover is this operator. We call this the complement. but we define to be the set of all elements in a universe such that X is not in the set of A. Turns out that operator is essentially doing the exact same thing as that one is. We'll make that connection even stronger when we're in the next section, 3.3. As far as the AND operator goes, skip that one for the moment. That's intersection, really, if we're thinking in terms of sets. And this is a very, very strong analogy. We looked at how we defined the intersection. We said the intersection is the collection of all elements X such that X is in set A, and at the same time, it's in the set B. And again, that's an extremely literal carryover. This just doesn't have to be sets any longer. And I kind of like the symbolism. This was the intersection symbol, and it almost looks like we're doing the same thing, but if it's logical propositions that we're using a logical operator, we just go like this. We make a hard angle, but it's a very, very strong analogy. And likewise, here's the one that I had to skip over. The OR operator, much in the same way, is defined, if we're thinking in terms of union, by using a logical OR in the same kind of way. In fact, with all of these things in set theory, if we happen to start chapter 3 before we used the set theory chapter, section 2.3, we could have directly used in place right there the OR operator, instead of just saying the verbal OR that we did there. But either way we've done do it, introduce it, we're really doing the same kind of exact thing. So if you like a big analogy, this analogy becomes even stronger as we move throughout the course. This is the tie-in. This is probably one of the major reasons we looked into sets, not just because of the interesting things we did in chapter 2. We'll be doing some practice just thinking about these operations and then getting to truth tables. But any questions at all, folks, with the definition so far? Okay, example 2 is really just getting used to thinking of how to work with these logical operators in ordinary language. So I have a couple propositions. It is raining. If we look out the window, we could say that's false for our region right now. Q is the proposition, it is cold. I would say that's true. That depends on how well you're dressed. But all we're going to do, whether these are true or false, is just write out what these would mean in ordinary words. So if we see a negation here, not P, we would just say, if P is the proposition it is raining, this becomes it is not raining. Hang on, Microsoft Word got upset at me for no apparent reason. There we go. So that's all that's going on with this particular example here. Does that make sense to folks so far on reading these out? Okay, next one is a P and Q. So we tie that together by looking into what the propositions are. It is raining, it is cold is the P and Q respectively. So writing this out in ordinary words would just be, it is raining. And, not meant to switch on there, we'll just hit it with the highlighter. It is cold. And likewise, no big difference here. This one is the OR operator. But let's pause a little bit on that operator for the moment. This one's a little bit trickier than you might expect. In ordinary language, this OR operator can be kind of confusing because usually we think in terms of exclusive OR in ordinary language when we're saying this or that. We don't necessarily mean both at the same time, but this OR is a little bit different. Let's take another look at this. It says P or Q is true when one or both of the propositions P or Q is true, and it's false when both P and Q are false. So when we go to write this out, keep in mind, this one's considered to be an inclusive OR. Because we allow for both propositions to be true at the same exact time. And that does carry over for what we saw in sets. When we said X is an element of A or X is an element of B, we included this element 5 inside the union. It's in the set both A and the set B at the same time. So when we go to write this out, I'd say you could write it as it is raining, or it is cold. And if you left it just like this, I would give that full credit. But if you want to be really, really specific by what we mean by this P or Q, you would add this extra thing. Let's put it in a parenthetical to say it's not required, but good thought to have at the same time. Or both. We allow for the outcome that both are true at the same exact time for the inclusive or. It's always an assumption, so you don't necessarily have to say that, but we'll eventually look into the exclusive or to contrast the inclusive one. Yeah, absolutely. Sorry, I should have clicked that chat a little bit faster. We'll also look into the exclusive or, which will only ever output a true when exactly one or the other is true, and false if they're both false or both true as well. Just trying to fix my penmanship there. Other questions at the moment? Okay, so example 2 is really all about just getting used to the operators, writing things out based off these two propositions. Now we'll extend a little bit further, and here's the exclusive or. It's written with a symbol that's sometimes called direct sum in other contexts, so if you've seen that before. So the exclusive or, P XOR Q, you could say for short, is true when one of P or Q is true, but not both. So that's going to contrast against our exclusive or. George asks, is there a N, A, and D, the other basic logical gates? I'm not too sure on NAND and the other ones. I'll have to take a look into that to get back to you on. So far on these notes, we're looking at the negation, we're looking at the AND, conjunction or disjunction, the exclusive or, and then we'll look into things like the implication, the biconditional statements to close that out. But I'll have to look into that to see if this comes up later on in the textbook. Okay, so I have a little bit of homework to get back to on that one. But other questions at the moment? Okay, definitely some exciting stuff. So appreciate the questions. Keep them coming as they come up. What we're going to look into next, putting all of these operators together so far, the ones we have on the table at the moment, is truth assignments and truth tables. The definitions get a little bit vague here. It says the truth assignment for a proposition over variables P1 through Pk is a function that assigns a truth to each value to a truth value to each Pi. I think that wording there is kind of tricky when they say variables. What we mean really specifically is atomic propositions is the way our author phrases this. They're going to be atomic in the sense that we can't break them down any further. For example, just the page above, this one's a compound proposition, but P would have been an atomic proposition and so would Q. We can't break that down any further. But this can be broken down into the proposition P, the proposition Q, and the OR operator. So when we say atomic propositions, things that can't be broken down any further, just a declarative statement and nothing extra going on. So our truth table is going to assign the truth value to any potential value for each of the atomic propositions that show up. So we'll write out a truth table for all of these that we have on the table so far to get a better feel and view of what's going on with the propositions and the logical operators. And this idea of truth tables turns out to be major and massive. We're going to look into this a lot in the next chapter as well when we do other operations. Any questions or comments so far? Okay, let's go left to right. This one's kind of a fun truth table because if you're looking at not P, the atomic proposition is just P itself. but it's undefined. So we're just going to give it a table that looks like this. Here's P. I want to have all possible truth assignments of that one atomic proposition P, and they would be true, false. That's it. That takes up all possibilities because there's only one proposition we're working with. But the thing we're dealing with is not P. We want a truth assignment for not P. So if P is true, the negation of P right here will give us a truth assignment of false. Really, we're just using the original definitions for the not operator. Likewise, if P happened to be a false statement, we have double negatives. The negation of a false statement would result in true. So that's our very first truth table starting out. Does that make sense to folks on the name of the game for writing up the truth table? Okay, let's extend further. These are going to turn into tools we use
Symbol is
over and
that?
over again. Sorry,
Sorry.
say again.
Next to the second P, is that like a bigger sign or no, is
Oh,
that the sign that's in front of the P? Sorry.
yeah, that's the not sign.
Oh yeah, sorry. It just looked like, yeah. Okay, thank you.
You bet. It's kind of hard to see all state because that's a really small just symbol kind of hanging out right there. Thanks for clarifying about it. Other questions at the moment? Okay. Next, we'll do the AND operator, this one. This one's trickier because it would involve two variables, as this definition here is referring to. It involves both P and Q. We're thinking of them as atomic propositions. So something along the lines of it is raining and it is cold on the earlier example. But now if you have two possible assignments for P, two possible assignments for Q, we will need 4 rows for all possible combinations of truth assignments for two propositions P and Q. So now the table gets a little bit bigger, but we can navigate this. We'll start with truth assignments for P, truth assignments for Q, then we'll put in the compound statement, P and Q. And there's no way that you have to definitely write this out, but if we're going to write out a lot of truth assignments, I would say pick a strategy that's just going to work for you, something that you don't have to worry about to think too hard, worrying if you didn't have every possibility, if you duplicate a row each time you write this out. And for me, the most sensible way to write these out is to start with true, true, false, false. So I have all possibilities of P. And now for Q, I'm just going to go true, false, true, false. So this row will be when they're both true. Here P is true, Q is false. Here P is false, Q is true. Last possibility, both P and Q are false. So I'm often going to go in this kind of strategy when there's just two propositions. If there's 3 propositions, we need 8 rows, and I'll show you the way I would typically do that in that kind of context. So pick a way that's kind of sensible, and I'd say stick to it so that you don't have to worry too hard again on this phase. So it's the conjunction P and Q. If both P is true and Q is true, we would definitely get true here. Any volunteers for the last assignments? Yeah, good call. From class, they're all false because the AND operator is very specific. Both P and Q have to be true at the same exact time to get the entire compound statement to output a true. And in every one of these rows, there's a false, 2 falses on this one, so we get false everywhere else. There's only a way to make P and Q true. Both propositions P, Q have to be true at the same time. Let me fix my penmanship there. So that's what's going on with the AND operator. OR operator is a little bit different, but any questions so far? Okay, let's write out another quick table. This part becomes kind of methodical. PQ, then I need 4 rows of outputs. So true, true, false, false, true, false, true, false. Now we have all possibilities. And now we're doing the conjunction, P or Q. Now, the idea with P or Q is this one will output to true whenever one or the other proposition or both propositions are true themselves. And notice that means there's exactly one way for it to be false, right? In this row, when both P and Q are false, this is your only false this time. True here for Q means the whole entire statement, P or Q, is true. True here for P means the whole entire statement is true as well. And because it's an inclusive OR, if they're both true, we output true on this one. Notice the kind of flipping we get. P and Q has true in one spot, false elsewhere. P or Q has false in one spot and true elsewhere. So that's kind of an interesting pattern to see in the truth tables. We have one last one to get through, the exclusive OR, but any comments or questions so far? Okay, again, this turns out to be a major tool that we'll use and take advantage of, not just in this section, but in the next sections as well. And for the exclusive OR, we just have to think about what was the definition above saying. So we'll tie it in with the definition. So first, let's write out that table, PQ. True, true, false, false, as before. Then true, false, true, false. Then P exclusive OR Q, or you can just say XOR, that's kind of a neat way to say it, I guess. Now, thinking about this one, it says the exclusive OR is true when one of P or Q is true, but not both. Thus, P exclusive OR Q is false when both P and Q are true. That's a surprise, so false here. Surprise if you're thinking in terms of the last OR table. And it's also false when both P and Q are false. I think that feels natural. You would get false here if both things are false as well. And these are the only ones that would output a true. One or the other proposition, P or Q, is true, gives us true here. So it almost matches this OR, and this is the only difference going from the inclusive OR to the exclusive OR, is you have a change right here in the truth assignment. Well, any questions at all, folks, on truth tables, thinking about them so far? Okay, next exercise is nothing too major. Here, we're just assigning a truth value to these compound propositions as they're defined above in the example. We'll think about the truth tables as well as we get through them. Again, these turn into be major tools. Let's hide that definition. That one turns out to be the tricky one we're going to look into later. P implies Q. So for the moment, just for a warm up on thinking about this table so far, let's read through these. P is true, Q is false, and R is true. Sometimes it's kind of hard on the eyes to just dig this out of the writing. It might not always be a bad idea to just write off on the margin. P, I'm going to think of as true. Q is going to have the output of false. R will have the output of true. And somehow just making that one small step right there, it actually kind of reduces the cognitive load of having to reread the statement and make sure you have the right assignments on all three things. It's more digging right here visually and kind of better presented here this way. So down the line, it says determine whether each proposition is true or false. If we say not R, but R is designated as true, then this one will come out as false. Let's give a justification for each one as we go. Since R is true. And it's pretty much the name of the game. This one is P or Q. Any volunteers for the truth assignment on this one? Yeah, absolutely. This one comes out true really just by reading P. It doesn't even matter what Q is. That could be true or false. It's irrelevant. The moment we spotted P as true, the whole thing is true altogether. That's kind of a weird deal sometimes when you really think about it when it comes to the OR operator. P could be a reasonable statement, something along the lines of, it is February 10th. And Q could be the most ridiculous statement you could ever conceive, like the moon is made of cheese. It doesn't matter. The whole P or Q statement together is now true, no matter how ridiculous off the wall the Q statement is. So pretty much you can just stop right there. P is true, the whole statement is true, and this is our justification. Since P is true. Now we're moving down to exclusive OR. This is P exclusive OR R. P is true and R is true. So this one comes out to false. That's our interesting row here for the exclusive OR. So we can say false, and for a quick justification, we can say since both PR are true. Again, it's not too major, but it's a lot of new definitions all at once. But think in terms of what the original definitions are, what the truth assignments are saying. This is really just looking at particular rows from our truth tables above to do the overall evaluations. So if this says Q and R, well, we look up what Q, R are. Well, really doesn't matter what R happens to be. The moment Q outputs a false, the entire statement here is false, irrelevant of the truth assignment for R. So we can say false, and the whole justification is since Q is false. And it definitely can get kind of hairy sometimes. We're going to look into bigger and bigger compound statements in this section, as well as section 3.3. So here, it might not be a bad strategy when we're thinking about this one is, first look up Q. Q is set to false. So that means this one would output a true altogether. Likewise, P is true. So we're safe on this one. It's an AND operator, so both had to output a true assignment to get a true output to the entire compound statement. So we can say true on this one, since both P, not Q, are true. So that's the rundown with our 4 operators so far. Any questions at all, folks, thinking about these truth assignments? Okay, now again, we're getting back into some interesting weird stuff that we really encountered quite a bit. Even in section 2.3, we made some statements back in the day, a few weeks ago, that probably still feels kind of vague and fuzzy in a certain sense. For an example, we made this big statement that, let's focus on this one. I like the subset equals operator. The empty set is always a subset equals to any set A, no matter what the set A happens to be. So that was a vacuous truth that we were mentioning. And this is what the next operator is all about. We're going to look into the implication and how vacuous truths come into play, making more sense of why this is always a true statement as far as the subset equals relationship goes. The implication is definitely where I probably would want to slow down in the reading, slow down in going through the notes, because it absolutely is tricky. That's kind of what this table is conveying as well. This is just a direct screenshot from our author's text. First, let's read through the definition. When it says the implication, we're referring to that arrow there. And often the way I would personally read this is if P, then Q. So I'm not going to ever try to write out Q is necessary for P. That's a completely equivalent statement. But I think it gets really confusing if you try to mix it up a lot. So for the notes that I write out and the exam questions I write, I'll be very direct, if P then Q. The homework can get tricky, so this is a good table to come up. If you see something along the lines Q if P, they mean the same thing. So the proposition, if P then Q, it'll be true when the truth of P implies the truth of Q. So you'll always get a true assignment there. In other words, P implies Q is true unless P is true and Q is false. That's the only way you get a false truth, a false truth assignment. We'll often say P is the hypothesis, or you could say antecedent, Q is the conclusion, especially if you're thinking in terms of, say, a theorem. So all of these statements would be conveying the same thing. If you are a legal US voter, then you are an American citizen. And you can restate that in a lot of funny different kinds of ways, which are all the equivalent statement. Again, if I ever have to write down an if P then Q type statement, or sometimes I might just say P implies Q for short. I guess sometimes we say it that way. This is how I'm going to make sure I do my writing in one or two kinds of ways, because I'm not going to try to hide the meaning ever. But ordinary human speech, it gets messy. So all of these statements are saying the same exact thing. First thing we'll do is hide part B and think about the truth assignment, and then come back to that part B. So here's finally the truth table for P implies Q. Place P and Q just like before. We need all possible truth assignments to those propositions. So let's go true, true, false, false. And if you have a different way you like to do it, again, I'll just be very careful to make sure it's all there, but just stick with your method and you'll be in great shape. Then let's stick with the method. I'll go true, false, true, false. And now the implication, if P then Q, or P implies Q. A good way to think about this is, I think an analogy is really helpful because this is a very tricky operator. Think of this as a promise or a pact you're making. So we promise that if P happens, Q is going to be the end result. So the only way that we're ever going to get a false out of this is if we break that promise. A false for P implies Q means we have broken the promise. So promise here just being an analogy for the very accurate and specific way P implies Q is defined. But if it's kind of vague and tricky the way we're going to be working with this is a really great analogy to think about just to internalize this information. So if P then Q, if P is true and then Q is true as well, the promise was not broken and we have a true assignment. But now let's think about this one. P was true, yet Q was false. That means we have essentially broken the promise. We said if P occurs, then Q will occur. But that doesn't happen here. P has occurred as true, but Q did not occur as a false. So this one is the false. And it turns out that is the only false that ever occurs on this entire table. The rest are true, and this is kind of weird. So if P then Q, if P is false, but Q turns out to be true, doesn't mean we broke the promise. Some other factor may have occurred, something extraneous to the proposition P that made Q flip to true. So this one is true, which is again a surprise in logic. This one's true as well. P didn't occur, so we had no chance to break the promise. And when we got a false here, we got a false here, so the whole thing is true. The promise wasn't broken, in other words. And we'll look into that again with two specific propositions, thinking about this analogy. But this ties into when we mentioned vacuous truth from way back in the day. Those last two rows are exactly what we mean by vacuously true. Well, any questions so far, folks, thinking about the implication? Okay, let's put this into the context of some really, really simple propositions. P is you sing, Q is my ears hurt. So kind of silly, but it's a great way to think about this one. The proposition, if P then Q can be expressed now, If you sing, then my ears hurt. So we think of this, the implication as being the if, then, and then the propositions P and Q are just slotted into that statement. So we're going to look into how P implies Q relates to the truth assignments that we gave above to determine how reasonable or weird they might look. And well, this is kind of an interesting follow-up question. Do the truth assignments make sense? So we'll try to answer that along the way. So think of this really carefully. Let's go row by row in the truth table. So we'll say here, P will get a true, Q will get a true. So what will that mean for the statement? You sing, I'll just say it kind of briefly here. My ears now hurt. And that seems reasonable. This is, again, we're thinking of it as a promise. I promise if you sing, then my ears will hurt. And if they're both true, this is an overall true statement. True coming from that assignment. But let's investigate what else can happen, particularly these last two rows. So if we change this to say P, true, Q, false. Let's make a semicolon. I think that'll kind of make sense with the formatting. What would that then mean? Well, we have the singing did occur, you sing, but let's see, this did not occur. Q is the outcome, my ears hurt. But if we set it to false, we can say my ears do not hurt. That means something went wrong. The promise was if P implies Q, but P occurred, Q did not occur, and this is where we get a false. It looks like the statement P implies Q, in other words, is just being dramatic. Nothing went wrong. Maybe your singing improved, who knows? But this would be given a false assignment. And that is the one and only one way to get a false on the implication P implies Q. Any questions so far going down the line on those truth assignments? Okay, next ones are the weird ones, the vacuous truths. Here we're going to assign P false, Q true, let's read that out. This would say if P is false, so if you do not sing, I'll write here, you do not sing, my ears hurt. And we consider that to be a true assignment. Why is that? Well, there is the implication or a promise that if you sing, my ears will in fact hurt. But if you do not sing, there was no way to show that promise has broken. Perhaps my ear hurt because it's an ear infection or something else is going on. There could be other external factors here. So we call this one true, but it's true vacuously because the only way to falsify P implies Q is P has to occur. So that's what's going on with this one. Any questions at all, folks, with the first vacuous truth row here? Okay, and I found this last row is not so bad. I think it's really row 3 that's the tricky one, at least in my mind. But this one says, you set both the proposition P false and the proposition Q false, which means you do not sing, my ears do not hurt. That would mean overall P implies Q is true because, again, we didn't have a way to show that you broke the promise that if P occurs, then Q will occur because singing didn't happen in the first place. There was no chance to falsify if P then Q. So this one turns out true. And it's a different kind of vacuous truth, but it would be considered a vacuous truth at the same time. There was no chance to falsify. So backtracking and looking at the overall picture, I guess that's backtracking a lot. It says the truth of P implies Q is true if the truth of P implies the truth of Q. But if there's no truth of P whatsoever, we don't falsify it. We'll say P implies Q is true unless P is true and Q is false. That's when we think of the promise P implies Q is falsified. And that's the one and only one way we get false overall and the implication. Well, any questions at all, folks, getting through this one? Okay, because the implication is a tricky enough problem, let's view it through this old idea from way back in chapter 2 once again. I have the subset relationship defined here from section 2, definition 28, or chapter 2 rather. It says A is going to be a subset of B. Here's the subset equals operator. I'll just say subset for short. When the following condition holds. If X is an element of A, then X is an element of B. When that occurs, that statement, A is a subset of B, is true. But we can kind of wind this back and connect it to the work we've been doing so far. There are propositions floating around everywhere when we were looking into set theory. So we'll define the proposition P to be the statement X is in A. Q is going to be the proposition X is in B. And now we can recast this whole thing into terms if P implies Q. But let's go back to B being any set whatsoever. It can be a pretty abstract set, or it can be a set that contains 4, 5, 6, something a little bit more concrete. We'll show concretely and compactly that the empty set is definitely a subset of B using our system of logic that we've developed already so far. Let's kind of think of this in terms of steps. So step 1, if we're going to be using all of our logical ideas so far, we need propositions. And so here they are. X is in A, Q is in B are the propositions that we have defined. But we need a logical connective. So we'll say A subset equals B means the following. If, let's write it this way, P implies Q. So that's the entire subset relationship in terms of how P is defined and Q is defined. So this implication statement is said here. These are completely analogous statements. If the P operation and the Q operation is what we mean by the subset relationship. So that's step 1. Just put this in terms of the logical connectives that we've defined so far. Step 2, let's take a look into the truth of P. That's going to be the major thing we look into. So for the truth of P, hang on, maybe for step 2, let's be a little bit more specific. Let's say for step 2, P is going to be the statement that X is in the empty set. Sorry, we should connect this to the actual sets on the problem itself before we get too carried away. So let's redefine P and Q in the context of this problem. And Q is going to be the statement that X is in the set B. So this set's right here. Sorry, I forgot to do that step 2 here to connect the dots. Now for step 3, this is the one I thought I was on. We'll look into the truth assignment of P. But here we can say just directly, P is false, since that set is empty. In other words, we are starting from a position of false immediately in the implication. we wind back to what our truth table was. Let's just screenshot this in for quick reference. The moment we get false right here, the entire implication P implies Q is automatically true. It's vacuously true, but it's the logical system we're working in, as well as computer science and mathematics. And so this statement, if X and A, then X and B, is now true. In other words, if you use the empty set and the proposition P is false, we are on this row. It doesn't matter what happens with Q any longer. Hang on, not the quite right row. I missed. We're either here or here, and it's irrelevant on what Q is. We get true either way. So our step 4, the conclusion, would be the statement. Therefore, empty set subset of B is true because P implies Q is true. And that's what we want to show, that the empty set is now shown to be a subset of any set whatsoever. If that's a real, true, defined mathematical set, that subset relationship holds. Well, the truth is, again, vacuously, we won't make a big deal out of it every single time, but let's say it one last time, vacuously. Well, any questions, folks, thinking in terms of this logical connective with this old definition from above? Okay, so this implication statement is nice and fun and useful, but we can even extend on this. Sometimes we want the arrows to go both ways, and we call that the biconditional statement. And so that's what this one is all about. This one plays a really special role in mathematics. You might have noticed if you're in any kind of math class and there's a theorem that mentions if and only if, it turns into a particularly useful theorem out of nowhere. If and only if we'll express in this kind of way, using the double arrow, as opposed to a single direction. The truth assignment on this one is tricky, so we want to be careful when we're thinking of example 7. The P if and only if Q is true when the propositions P or Q have the same truth value. Say they're both true or they're both false, would mean P if and only if Q will output a true result. So if we write out the truth assignment for this one, here's what it would look like. Here's our proposition P, proposition Q, then the rest of the table as usual. True, true, false, false. And then true, false, true, false. Finally, P, let me fix that arrow there. P if and only if Q. So looking through this really carefully, we have a true on P and a true on Q. That would mean the biconditional would output a true altogether. So that's what it's saying here. We'll have that if and only if will output a true when both P and Q have the same truth value or same truth assignment. So the moment there's a false, we get a false here. There's another false on this one. So we'll get a false here. And this is the one that's kind of easy to miss. P if and only if Q, if they're both false, the whole assignment is true. So that's what's being mentioned on this part of the definition here. So that's what's going on with P if and only if Q. Any questions about it so far? Okay, again, it's kind of an interesting operator altogether. They'll have a lot of interesting uses. But for the moment, just to kind of bring everything together, we have a lot of logical operators on the table so far. 4 basic ones, then the implication, and now the if and only if. Here's where I made a quick edit just to make the problem a little bit more interesting. So I'll try out one other example looking into these kind of truth assignments. Then we're going to end on a slightly more challenging version of just writing things down in ordinary words using our new operations, the biconditional, the implication being the major one we'll highlight, and kind of reviewing all the rest. Then we'll make a big change when we're going off into the next section and start using these truth tables to look into bigger compound statements. We're going to look into things along the lines of logical equivalence, tautology, satisfiable versus unsatisfiable. The 3.2 just kind of sets the stage for everything else we're going to be doing in the next section. Okay, so let's give this a try next. With the truth assignment defined here, here's what we have going on. We have P is true. Proposition Q is going to output a true. That's a horrible Q. Let me try again. Proposition R outputs false, and proposition S outputs false as well. We want to determine whether each proposition is true or false. So this one's the biconditional, the same one we have the truth assignment above. It starts out with a compound statement here, not Q. Let's look at Q, it's true. So this one will be a false on the left. And S has the truth assignment of false as well. That just means we're on this row. We can say overall, this one is true. And the quick justification is, since this one's about having the same truth output, so we'll say since both, not Q, S, are false. So kind of similar to the earlier exercise, just more stuff on the table for this one. And let's think about this one next. R implies S, or we could say differently, if R, then S. Anyone see what truth assignment we should put down on this one? Yeah, absolutely. In fact, the truth of this one doesn't even depend on S whatsoever. This one is automatically vacuously true. So these are pretty tricky ones. If you have an implication going here, but you notice you start from false, there's no way to falsify the promise. If R occurs, then S occurs. So we'll say this is true automatically, and our justification is since R is false, there's no possible way to make this a false statement any longer. And here's another one. This one's a little bit trickier with the compound statements. The negation of R implies the negation of P. So let's break this down a little bit further. R on the right is false, so that means the negation of R is true. Now, this could be a potential broken promise if we have false here. Look at P. It is true, but so that means the negation is false. And this is the one and only way if P then Q as an operation becomes false. So we'll say here, false, since P is true, and, oh, hang on, that's the wrong operator. Since the first one, that's the not R is true, and not P is false. My justification can't be very small in this one. Those two exact things have to happen at the same time in order to get that false output here. Okay. Now we have another biconditional coming into play. This one came out as true with a false and a false. But let's be careful. These are becoming bigger and bigger compound statements. You might have noticed we're very rapidly approaching an order of operations kind of issue as well. So that's part of the work we're going to look into next. What is the logical order of operations that we would have to take? But parentheses, just like an ordinary algebra, does clarify a lot of stuff. If I drop the parentheses, they might still have meaning, but now we need essentially order of operations to tell us what the definite meaning should be. Well, this one is P and R. To get a true here, both P and R have to be true at the same time. So let's look that up. We go true and false. That means they have different truth assignments. This one is false altogether. And here's our exclusive OR. R comes out as false. Q comes out as true. That means back over here, this one's true. If exactly one is true on the exclusive OR, you get true altogether. But notice the truth assignments are different, and this one is at biconditional. In the biconditional, those are the one of two ways you could ever get a false if the truth assignments come out different. Again, this one's surprising. False if and only if false is true for the biconditional, but this is the one that goes bad. So here we'll say false over all is the truth assignment. And for the justification, this one is since P and R is false, and R exclusive OR Q is true. If they were both true, we would have had a true output to the biconditional, as well as we had a both false. But if you flip the values, whether it's false true or true false, we get a false assignment on that overall compound statement now. Well, we did it, folks. That's all the operators on table. I feel like this notes does feel like it flies by fast after defining so much stuff at once. But we're going to be citing these tables, referring back to them constantly as we're working through the next section and even beyond. Any questions about example 8 before we look into the last one? Okay, so this next one is the last one for these notes. I have three propositions. It is winter for P, it is snowing for Q, and the neighbor is mowing the lawn for R. So now 3 propositions on the table. What we're going to do for each of them is just write them out using ordinary words. Some of them are kind of built up, so we have to be careful. And some of them are extremely specific. This one's an exclusive OR, so we have to convey that when we go to write this out. Let's go down the line. On this one to start out, here's the proposition R, but we're starting off with the negation of R. So we could write this out as, because it's an implication, I'll begin with if. Then write out not R. If the neighbor is not mowing the lawn, then I want to really organize this very concretely and specifically in terms of an if-then. So I'll go here, then. And that's the whole essence of the implication, the right arrow statement there, the implies operator. Then what happens is P, sorry, let me target my highlighting a little bit better. P is the statement, it is winter. So we'll say then, it is winter. So probably it's a neighbor with just a really high work ethic with the lawn. If they're not mowing, that means one only thing, it's winter. So that's what the not R implies P would mean. Any questions at all, folks, running through part A? Okay, ran out of colors for Q, so we'll just leave this one uncolored. This one is the biconditional, if and only if. So you have to really make sure that we convey that in some way, somehow. But really, it's not too bad. We're just going to read out the statement. It's just a matter of going to the proposition, looking up what the declarative statement is, and make sure we capture the essence of what the logical connective is that we see on paper. So P is the statement, it is winter. But this is a biconditional, so we really have to capture that. I'll just say here verbatim, if and only if. And just as a quick aside on this, the statement if and only if is such a common statement coming from the biconditional here that people started writing it out this way. If with 2 letters F. And that became such a humongously common shorthand, it actually made it into the Oxford English Dictionary pretty recently, not, I think, a matter of decades ago, but that's pretty recent. So this is a standard shorthand if you'd like to use it. Really has to be exactly two Fs or you have a different meaning. With one F, you might be meaning this instead. So we'll say it's winter if and only if, statement Q, it is snowing. That's how the statement would read out in ordinary words. We're not too worried about the truth assignment. It hasn't been snowing out here in Idaho Falls for quite some time. I assume same in Pocatello. But that's how we would read this out, just saying it in ordinary words. Well, let's think about this one. The negation of P and Q implies R. Or you could say, if the negation of P and Q, then R. We have to convey this in a way that captures three logical connectives, a negation, and operator, a conjunction, and an implication operator all in the same time. I know there's a lot of ways to say this. As long as you say it that conveys all those things, and there's zero ambiguity, you're all set. But that's what we're trying to eliminate when we go to write this statement out. We're trying to eliminate ambiguity. So there can't be 5 different takes on what you just wrote. It has to all connect back exactly to this. So let's make a statement here. Our statement cannot have ambiguous meaning. In ordinary language, again, that's kind of tricky sometimes. Any volunteers for a take on how to write this one out?
Okay, so I have a way of solving this. Can you hear me?
Yeah, yeah, you're coming
Okay,
through great.
I have a way of solving this, but it's from a different logic class, so I don't know if that's necessarily valid for this case.
Are you thinking De Morgan's laws?
I believe so.
Yeah, if you use De Morgan's laws, you can distribute this through and change it up into not P or not Q. And that's great, right? Because it really just simplifies the statement way, way down if you go that route. So is that what you were thinking along those lines?
Yeah, I just don't know if that's appropriate for the current context of the class.
I would say absolutely. This is something we're going to look into in the next section, 3.3. The
Okay.
interesting De Morgan laws is just a part of the batch. And if you did that on this assignment 3.2, and we haven't even gotten into 3.3, that's perfectly fine. You can't lose points for knowing stuff is kind of the theme of the class. That just seems not very sensible. So let's give that solution as well. We'll go for 2 solutions on this one, starting with your suggestion. Let's break this down. Not P and Q. I have a big claim to make on this. Not P and Q is logically equivalent, that's a symbol that we're going to use later on, to not P or not Q. And we've been using set theory as well as an analogy to all these logical operators. And you know what? It works in set theory as well. The complement of A intersect B is in fact equal as sets. So I'm not using the triple bar here. So we're using set equality as we defined. This is the complement of A union the complement of B. The analogy between logic and set theory is extremely, very, very tight. So just switch up if you're dealing with a logical connective and an or, intersection union, and whether they're propositions and sets, it's the same property. So if we go this route, this is a much easier statement to convey. We can say, I'll start with this arrow. If, and somewhere I'm going to put in a then, so I'm taking care of the implication first. And now we're going to the negation statements to massively simplify this. Let me follow the color coding I already have here. Not P would say, if it is not winter, now we have a logical or in the problem, so we'll switch this one to or. Now go over to Q, or it is not snowing. This is an inclusive or, so if you want to, you could put in a statement or both to convey that. Again, that's the overall assumption in this class, so if you leave it like this, that'd be completely fine. Then I'll go over to then. So the if then is essentially taking care of this entire implication statement. We have the statement are, the neighbor is mowing the lawn. And I like it. I feel like this is going to be a lot more simpler for what I'm about to write for the next take on this one. But let's call this one solution one. Again, if there's no ambiguity in the meaning, then it's a perfect solution for this kind of problem. Other questions or comments going that route? De Morgan's laws here. Okay, it leaves the question as well of how would we write this out if we are just dealing with this pretty convoluted looking compound statement without trying to simplify it down to that. So probably the way I would go is start with the implication again, if, and then I'll have it then to connect with it later on. Then the next thing I would take care of is that entire negation statement. So I'm going to say if it is not the case that, and then that's going to be another compound statement. So I'll go if it is not the case that, and that's a lot of words for a negation symbol, but in trying to say this in a way that doesn't have any ambiguity, it looks like it's taking a lot of words. If it's not the case that, now we have to write out P and Q. So starting with P, it is winter. Here's another connective, and Q, it is snowing. I'll go comma, then. Let's just pause on what we have so far. So the if then takes care of the implication, the right arrow. It is not the case, takes care of the negation symbol. And then in my feeling of the way it's written, after saying it is not the case, everything thereafter is kind of in a verbal parenthesis now until we hit the comma. It's not the case, it is winter and it is snowing is the P and Q part of the problem. We have then, and then we write out the statement are. The neighbor is mowing the lawn. Let me fix that a little bit. So again, there's lots of ways to potentially write these out, depending on the way you decide to designate the negation symbol verbally, or if you're using other tools like De Morgan's. So we'll call this one solution two. Probably this is the idea the author had for this particular problem, but any questions or comments so far? Okay, and again, this is the major content of what we're getting into section 3.3. If your big question is, why in the world is that true? Well, it's going to be a matter of truth tables and truth assignments. My claim is, if we look into the truth table for not P and Q, and look into the truth table for not P or not Q, you will find that they have completely identical truth assignments. That means they're logically equivalent, and this operator works as expected. And verbally, this is what it's saying here. I think it's harder to show verbally that this statement is conveying the same information as this statement. It's a little bit tougher. But once again, you can also see it through Venn diagrams on what's going on with sets. It's going to be the same kind of ideas. But to finish off the notes, let's get to the exclusive OR problem. Kind of save the nastier one for the penultimate problem here. So here's the exclusive OR one. P exclusive OR R. The only thing we have to be very, very careful of is we convey the exclusive OR when we go to write this out. But we can start off just as before, looking up the definitions. It starts with P. So we can say, it is winter. Now we're writing this out in ordinary words, so we can't say exclusive OR. That would be a weird thing to say to a person passing by in the streets. It's either winter or exclusive OR are the neighbors mowing the lawn. So in ordinary words, we would still just say or. It means we have to tack on an additional statement. So let's go to R first. The neighbors mowing the lawn. And then finally, the exclusive OR is conveyed when we just say something along the lines of, but not both. Or we can make a really long form statement and say, not both it is winter and the neighbors mowing the lawn. But it's okay to just abbreviate like this. So these two elements, the fact we said or, but we're directly saying not both outcomes at the same exact time, conveys the exclusive OR in this problem. Well, that's the rundown so far, the big introduction to all these logical connectives. Any questions or comments at all, folks, with these last two parts? Okay, just to give us a preview of what we're getting into for the next section when we come back on Thursday, we're building. Here we're going to be looking into, let's see here, tautologies is going to be our next big context. Once we get beyond tautologies, we're going to be looking into notions of the standard hierarchy for logical connectives. Then we'll look into logical equivalence and introduce some really important ideas when it comes into logic. This is considered an implication. We'll also consider the converse, the contrapositive. The contrapositive is going to play a really special role in some of the work that we're going to do later on. And finally, tie it all together by looking into things like De Morgan's laws to determine if we are looking at things are logically equivalent and so on. But, the big idea for just about every single thing we do here, whether it's the De Morgan's laws we just looked into, is we're just going back to stuff like this. This is going to be the major tool. This is what we're going to be working in the exercise for 3.2. And we'll be connecting the work on these truth tables for understanding these things, the tautologies, logical equivalences, and so on. But any last questions or comments at all, folks, before we call it a day today? Okay, well, have a great afternoon, folks. I'll be sure to start off class next time looking into the NAND operator and other logical gates and so on to give a better response to that. But have a great afternoon, folks. We'll be in section 3.3 next class.
Thank you.
You bet. Have a good one.